Good morning. Welcome to Control Systems webinar and seminar. We earlier saw in our analysis about the Routh-Hurwitz criterion. Routh-Hurwitz criterion is one of the computational numerical method for control systems in determining the roots of the polynomial, whether they are going to be real negative parts or complex negative parts. But why we want that analysis of the control system roots of Routh-Hurwitz? It is because we want to see whether the system will be stable with that roots. Roots of the polynomial are going to determine the function entirely, and the control system behavior is dependent on the function or the polynomial being selected. We saw the polynomials cube 6s square, then 12s plus 8. We want to see in a shortcut method to determine the roots of the polynomial. We earlier saw that the roots will be given by eigenvalues. In our area schools and the preschools, we might have heard about eigenvalues. The eigenvalues are going to give us some roots of the equation. The similar manner, we can convert this particular polynomial into a type of determinant, and then we can derive at the values, or we can derive at the primary, secondary and tertiary roots. So this is how characteristic roots of the polynomials are obtained from the equation. We will see the simple equation now, and how it is being manipulated for its roots. Then we will come back to the concepts of the control systems. What you are seeing is a polynomial for which I want to compute the roots. I have the polynomial 1 square plus 6, 1 cube is 6 square plus 12s plus 8. Now I want to determine the roots in the determinant method, for which I have to separate the coefficients. How I have to separate the coefficients? But first I have to take the coefficients in an order such that I have to separate them, then I will take the determinant form. So I will separate the coefficients now into even, odd, even. This is how I can take other way I can take even, odd, even, or there are two ways: odd, even and odd. Now I have to see this even, odd, even. That means I will take my even terms. What are the even terms here? 6 and 8 I have. So I will take the 6 and 8 as a determinant 3 cross 3. So I want to find the determinant value. Now I will take the odd terms. Now I have finished even. I have to take the odd. That means I have to take the 1, then this 12. 1, 12. But is this a 3 cross 3? Which is not a 3 cross 3. I have to make it a 3 cross 3 because this is going to give me 3 roots. That means a tertiary and secondary and then the primary. This is how I need to make the roots of the equation. For this particular roots of the equation, I have to derive in a manner such that I have to add or append zeros to the existing determinant or the matrix I am constructing. I am constructing a 3 cross 3 matrix. Now I want to see the value of this particular determinant, that is 12 into 6, 72 minus 8, that is coming to somewhat 64, which I saw and worked out here to maintain the stability or to say or ascertain that it is a stable control system. However, here we are not going to do that as an additional task. Again, we have to repeat this particular even, odd, even. That means I have even, odd, even. This is a tertiary determinant. That means tertiary is derived from all this secondary. The secondary will be very accurate, but tertiary will be derived from it. So if I have to derive the tertiary, then I have to repeat these terms 6 and 8 here. It will complete the determinant for the tertiary. So I will call it as a 3 tertiary Then what is a secondary? Secondary is exactly derived from the polynomial. If I want to have a secondary determinant, then the root of the polynomial will be 6, 8, 1, 12. That's all. This is a solving this determinant will give me a secondary. Then what may be my primary? My primary is 6. So this is my primary. My primary is this, and I am getting my secondary root, from which I am constructing my matrix for the tertiary root, which is solved as a determinant. This is how I obtain the roots of the polynomial for the Routh-Hurwitz criterion. This is one method of determining the roots of the polynomial with the Hurwitz criterion using determinants without computing like this. I want to use determinant method. This is one type of analysis to say that I have the primary as 6, secondary as solved value, that is 64, and tertiary will come to some value, right, after I solve. So my primary root is 6, then secondary is 64, then tertiary may vary, but this may vary in signs, this may vary in amplitudes, that is magnitude, and the variation of their magnitudes and amplitudes are very important in saying what they are going to do. So I can say that the values of the coefficients of a polynomial, namely if I say this as a polynomial, then the value an, then the an minus 1, etc. to a naught here, there is 1. The values of the coefficients of the polynomial is going to determine the stability of the particular polynomial, and the stability is not just for the polynomial, it is for the control system associated to the polynomial. This is what I want to prove using determinant method, which is quite advanced from simple solving quotient method. This is quotient method of rearranging the polynomial into Routh-Hurwitz table, but this is a determinant method of Hurwitz analysis along with the Routh criterion in extracting the coefficients or roots of the polynomial in determinants form. This is one simple example we have seen. Now we are going to see some concepts related to the same. Once again we will have a look at that polynomial. So we have the s cube plus s square plus 12s plus 8. I have solved it in terms of even, odd, even, or the other method may be odd, even, odd. So this is for constructing the tertiary, not the primary. So I will now elaborate on the control system concepts which are going to be relative to the stability condition and other criterion which are going to be valid for the control systems. The Hurwitz condition, we saw the matrix method of solving the polynomial, wherein we got the equation which is called as a characteristic equation, and when we say that the equation has got an order, there is a difference between order and degree in an equation. We saw the degree of the polynomial was the highest power, but now when we want to see the order of the polynomial is not going to be given abroad, but we are going to derive from the characteristic equation. What we see, the polynomial is just a characteristic equation for which the order has been derived from the tertiary determinant. So we saw the tertiary determinant which is going to give us the order. Now if we want to give the tertiary determinant of a polynomial which is going to take the degree power as s power 4 instead of s cube as seen here, s cube plus 6s square plus 12s plus 8, this is one thing. But if I have s power 4 term before s cube, then the order of the tertiary determinant may be a 4 cross 4, which is very important for the determinant tertiary determinant resolution. Hence, as my polynomial gets complex in terms of degree, it is going to affect the order. That means it is going to affect the order of the matrix which is constructed from the polynomial. So, order of the characteristic equation means not the order associated to polynomial. Polynomial has degree. So, degree of the polynomial is associated with the order of matrix or the determinant which is going to be derived from the polynomial. So this is called the complete Routh-Hurwitz stability condition method by use of determinants. To elaborate well on this particular stability and some other conditions, we will see another example so that we get a better way of solving these equations. I have got the same equation. Now, having said that the order is going to be derived from that of the complex polynomial, we will now see the equation with the same degree. So, it is a polynomial with the same degree. I am calling it as an equation because we are using the term equation more than the polynomial. So, I have 4 square plus 8s plus 12. Now, I want to split this polynomial as a derivative. That means I want to split this polynomial into odd and even so that I partially split them into two derivatives. What are the two derivatives possible? If I look at the odd terms, I have 1 into s cube plus 8s. If I look at the even terms, I have the 4s square plus 12. So this is how I have split up the polynomial, which is a function of s, into two functions, right. Now the two functions are derived from a function, but the function is applicable to a characteristic equation. I have the polynomial. I call it as a characteristic equation because I am going to derive from the characteristic equation two functions, namely q of s1 and q of s2, which are going to split the polynomial into odd and even terms. And then from these functions, I am going to derive some other method such that I determine the stability condition for this particular polynomial associated to the characteristic equation. So how can I do that? So I want to take the highest. So I have the first polynomial which has got highest degree. Here it is a 3. So I can divide the first polynomial by the second polynomial. I can divide the second polynomial by the first polynomial because if the degree is lower, I can't do that. So I have s cube plus 8s divided by 4s square plus 12. Now this cannot be easily done. So it has got some resolution. It has got some resolution in doing so. How the solution is being done? For solving this particular fraction, this is called as a fraction method or polynomial fraction. We have got a solution to split. If the polynomial is split into odd and even terms, we have got the solution of splitting these terms such that we arrive at the coefficients corresponding to this as a series which are going to be infinite. So I am going to convert this particular series into a infinite series method. So we have the finite series as well as infinite series. If I do so, I take the first term as 1 by 4 into s, because this is a s cube by s square, so I have the s 1 by 4, but it has got a method. In doing so, it is like 1 by some a value a1 into s plus 1 by a dot a1 then s plus 1 by a1 s square plus 1 by, like this it will continue, right? So it will continue like 1 by 1 plus this value plus, like this it will prolong this particular series into infinite series. However, we just have two functions, hence we don't need this particular term, it will become a finite one. So we can construct an infinite series if the series is continuing in the polynomial. However, here if we do not need the functions more than these two functions which are constructed from the polynomial, then this becomes finite. So in a similar type of equation or a similar type of resolution, I get the particular solution for this polynomial as 1 by 4s. The first one is very easy to compute. It is just on looking into this one, we can compute the s cube by s square. So 1 by 4s we have computed. Similarly, this is the primary, then secondary will be 1 by 4 by 5s plus 1 by s by 12 into, that is 5s by 12. So we can have 1 by 4s plus 1 by 4 by 5s plus 1 by 5s by 12. This is a method of solving this particular split function into a value which is going to end up into a finite series or infinite series. So why we want to do this as a finite series or infinite series? It is one type of method in a fraction. We saw the determinant method, it is going to give us a value, but this method is giving us a fraction. That is the only difference. With the fractions, we can say that this is going to be a stable one or unstable one. So we have seen there are so many methods in solving a particular polynomial, by splitting the polynomial or by deriving the tertiary determinant from the polynomial, or by constructing a Ruth table for a polynomial. These are several methods, but we cannot say that one method is very best suited for analyzing a particular polynomial, whether it is stable or not. So all these methods have been simultaneously analyzed to ascertain that a particular polynomial will be stable or not. To avoid such a complexity, we went for Nyquist plot, which also had got some pole zero plots on a complex plane. The complex plane, diagrammatic plane, is going to analyze all these roots, and then it is going to say, based on the poles and zeros, whether this polynomial is going to be stable or not associated with the control system. Hence, instead of having 2 to 3 methods like Roth table method, then partial Roth fractional method, then Routh-Hurwitz determinant method, 3 methods for analyzing the polynomial to say the polynomial is stable or not, we could go for a complex J-plane plot and call as a Nyquist plot, which will also say that there is a stability path which is going to decide whether the polynomial is going to be stable for the control system. Thanks for listening. We will come back with the Nyquist plot in the next session to continue.